All right, guys. So welcome to our last lab of the semester. So this is on analyzing an RL circuits. So in terms of then what we have for the RL circuit, R is something that you already familiar with. So this is the resistor. Now imagine what we have here is if we have a battery, some kind of EMF source, and let's say we have a switch here, some kind of open switch, and let's say the system is connected to some kind of resistor. There you go. So this is a simple circuit with just a resistor. Now, what we have here is when we close the switch, as soon as we close the switch, then the current in the circuit, since we close the switch, there's a closed circuit, so there's a current in the circuit that has a sort of like the value of I. I is being basically the current that in a way is right away instantaneously maximum value. So this I is basically its maximum value, and it's given by the voltage or the EMF, right, of the battery divided by the resistance in the circuit. That means with the battery and the resistor combination circuit, the current after closing the switch right away is its maximum value. That means the current goes from zero to max nearly instantaneously. So it's almost instantaneous process. What we have here is a new device. The L stands for the inductor. I don't know where you find L in an inductor, but it's the value of the inductor. All right, so that's the inductor. Inductor is a device that is specifically designed to provide inductance, which is similar to capacitance or resistance in the circuit. So in the previous lab, we talked about Faraday's law of induction, and we learned how a coil of wire can um, resist the change in flux by providing induced EMF, induced, a current, um, trying to oppose the change of the flux through the loop. Now, this inductor is basically a similar device, usually a solenoid, that is basically just a coil of wire, so some n number of turns, and it's specifically designed to, again, act like a device that opposes, for example, this type of instantaneous increase of current from zero to maximum. Okay, well, this L for the inductor, I was obviously caring about in terms of where do you see L in the inductor. There's no L in the inductor, but the L is after a lens. Lens, if you remember, we talked about there's a Lenz's law that allows us to conceptually understand the induced EMF, induced current direction. So L is basically is pretty much given in terms of in honor of the lens. All right. So what is the difference in the circuit when we include this inductor as a device? By the way, as I said, right, the inductor is usually some kind of solenoid, and which is basically some n number of turns. So then this is sort of like, let's say, how we represent inductor in the circuit. Okay, so L is kind of like represented that, and in the circuit diagrams, then what we have here is, so inductor when is added with this resistor. So let's say here's my circuit that I just had a minute ago. So actually, let me put this switch over there. So think like this. If this is then the resistor, and for example, if I add an inductor like this, then once I close the switch, the current doesn't go to its maximum value instantaneously. Okay, because as soon as there's a current going from zero to some value, that means now right away you have a change in current in the circuit. An inductor will then try to prevent it. So inductor as a device, basically it tries to resist the increase of the current to its maximum value by inducing its own current, its own EMF, just like we discussed in Faraday's law. Now, in terms of then this current that we have in the circuit will eventually reach its maximum value, but then this is basically going to be some time varying current, no longer some right away maximum value. That means the current as a function of time will increase. And one of the things we're going to see here is that that increase is basically going to be can be described in terms of, if you look at the current as a function of time. So it's pretty much going to be something like this until it eventually reaches its maximum value. It kind of saturates to its maximum value. All right, that means we're going to be exploring in terms of a circuit that, by introducing the inductor, this device, right, where L is the inductance of the inductor, we're introducing a device that allows us to basically kind of like a control a current. So, for example, if there is some kind of sudden spike in current that can be dangerous to the circuitry, uh, the inductor can prevent that by slowing down the rate at which the current is increasing. Okay, by inducing current, EMF in the opposite direction to slow it down, its increase, or slow down its decrease, depending how the current is changing. That means I'm talking about the current basically from the battery, right? Now, this current, let's call this I. Then when it gets to this junction point here, then what we're going to have, there's going to be current, let's call this current through the resistor R, and there's going to be another current then through the inductor L. Okay. Now, what we have here is, if we look at then the circuit, as soon as we, let's say close the switch, and by the way, we can always assume that at t equals 0 is when we close the switch. Okay, so that's when we close the switch. That means before that, at any time before that, we usually present at t less than 0, just like sort of like the capacitor, right? T less than 0 just means before we close the switch. The current in the circuit was 0. There was nothing. So the current was 0, the switch was open, and at t equals 0, we then close the switch. Okay. So once we close the switch, then what we can say here is the current in the resistor is 0, the current in the circuit is 0, and current in the inductor is also 0. Okay. Then, as soon as we close the switch, the current from the battery is distributed, is provided to the circuit, but the inductor right away starts resisting that. Or it's right away start resisting that. And one of the things we're going to be able to do right now is derive an equation for the current. Again, that's kind of like I give you the graph kind of ahead of time, but we can derive the equation for the current and see it, ourselves, why the equation basically behaves the way I have described in the graph. Okay, now think like this. So in terms of then, if I look at this particular loop, I can see that I have two devices, a resistor and an inductor, and then both of them have a downward current. So then if I have some kind of the Kirchhoff's rules, or using the Kirchhoff's rules, I have like a loop rule where I would take then and have some kind of a counterclockwise loop, and use that to derive the, equation for the basically the potential difference for those devices. Remember, the Kirchhoff's loop rule tells me that potential difference then across a resistor plus potential difference across the inductor, if you add them together, you get 0. It's conservation of energy, basically. And the potential difference across resistor is going to be then just remember, just like an equation for the potential, which is current time resistance, but it's going to be a drop. So it's going to be current I, and by the way, I'm going to start writing it like this since it's a time varying current, and so IR and IL. So it's going to be time varying current times then the resistance value, and it's going to be negative, but because if I go clockwise, counterclockwise for my loop, counterclockwise means that as I go through the resistor, since I kind of like my loop, right? As I go through the resistor, I'm going in the direction of the current, means my loop equation gives me a dropping potential. For the inductor, I go in the opposite direction of the current, which means that I have a gain of potential. So then the equation is negative IR, the current through the resistor times resistance, then plus then equation for the potential difference of the inductor. Now that is equation that will give me potential difference across inductor, and that's given as L, which is the inductance, then times changing current through the inductor as a function of time, di dt. Okay, adding those two together, we get 0. Now, remember, this point here is a junction point. This is a junction point, and junction point always have the net current equals 0. That means I can say that this is the maximum current, which technically I can write it, since maximum current is constant, I can write like this. This is the maximum current. And I can say that maximum current is going to be equals to, because you can see, right, the maximum current is the current kind of comes into the junction point and it's branches out. So that means it's equals to current going to the resistor plus current going to the inductor. Okay. Now, coming back to this equation, let's call this equation 1. I can have then this equation 2 where I can rearrange and solve for the resistant current, which will be the maximum current minus the inductant current. Okay. Then I come back here to equation 1, and replace current to the resistor with that, this difference of the maximum and current to the inductor. So it's going to be negative I max minus current to the inductor, then times the resistance, then plus L times DIL dt, and this is equals to 0. Okay. Now if I rearrange, it's going to be L DIL dt is equals to negative. Well, it's negative. It's going to go other side. It's going to be positive. So it's going to be then I max minus IL, then times the resistance. Okay. Now what we do from here is we cross multiply. So basically, multiply both sides by dt, which cancels that. So then we have then DIL equals I max minus IL, then R dt, then divide both sides by this difference, I max minus IL. Okay. So then finally what I have here is this. So DIL over I max minus current to the inductor equals just, and divide, sorry, there was a L, divide both sides by L as well. So then becomes R over L dt. Okay. So that means this is sort of like, let's say, what I have right now. Because from here, what I'm going to do, I'm going to then integrate both sides. I'm going to integrate both sides and basically find the solution of this. Okay. So the right side of the equation is relatively straightforward. This is basically L over R over L are constant. So it's going to be R over L. So then integral of just dt. So this is just going to be R over L times T. Okay. Now, the left side, then what I'm going to get out of that is going to be negative ln of I max minus IL divided by Imax. Okay. So this is the left side, and it's equals to R over L on the right side. Okay. So then if we rearrange this, that means, if I take that and I take the E of both sides, also incorporating the negative. So I can take, let's say, before doing that, if I take like the negative to other side, so then my solution will be current as a for the current through the inductor is equals to the maximum current, okay, then 1 minus e to the negative r over L times t. Okay. And this is the equation for the time varying current through the inductor. This I over here is a time varying current equation. Okay. That means this tells me that how the current changes. Okay. So what I have here in the parenthesis, this quantity or this format is a format of, increase of a current as a function of time that will have a shape like this. Okay. So that's basically that's why the graph, look like that, because current as a function of time will have shape like that, where this is basically my Imax. Eventually it will reach Imax. Now, one of the important things here is, if I look at this ratio, R over L, this ratio is defined as 1 over tau, or I can say that tau is equals to L over R. Okay. This tau is known as a time constant, just like the time constant for the capacitors. So this represents the change in the current by about 63%. So how long it will take for the current to change by about 63%. Okay. So this is again time constant. So if I rewrite this equation, I can rewrite this as IL is equals to Imax and 1 minus e to the negative t over tau. I can basically write it in terms of that. Okay. Now, from here, what we can do is, if I'm using this equation, you can see that at t equals 0, indeed the current through the inductor was 0, because if I'm writing some current to the inductor equals Imax, then 1 minus e to the negative 0 over tau, that means it becomes e to the 0. E to the 0 is 1. 1 minus 1, this is 0. That means the whole thing is 0, which verifies that current at t equals 0 is 0. And then it increases as a function of time. And what we have here is that increase basically gives us pretty much a graph that has a shape like that. Now, one thing we can do from here is to do the data analysis, kind of do a reverse engineering a little bit, because in our experiment, what we're going to do here is to see if I divide both sides by Imax and take the ln of both sides. That means I have IL over Imax equals 1 minus e to the negative t over tau, right? So if I rearrange, where I have then move this one to the left, this one to the right, then what I have here, e to the negative t over tau is equals to 1 minus IL over Imax. Okay. Then if I take then ln of both sides, then what I will get here is, negative t over tau is equals to ln of 1 minus IL over Imax. Okay. Then if I just solve for the t, then t is equals to negative tau, then ln 1 minus IL over Imax. Okay. All right, and then The last step will be t is equals to tau ln, move the negative into the, into the parentheses, will be negative IL over I max minus 1. All right, so now, what is the reason of getting this equation? Well, this equation is the linearized equation for the changing current. That means if we do an experiment, for example, remember that circuit we had. Here's the battery, here's a switch, and then there was a junction point, then there was a resistor R, and then there's an inductor L. Okay. Now, as soon as I close the switch, then EMF will, basically, if I can measure the EMF, that means, put some kind of voltmeter here that measures the voltage, and then some kind of ammeter here that measures the current. Then I can get a data where how the current across inductor, right, changes as a function of time. Okay, so remember, when this is 0, this is 0, but then as as a function of time, obviously it will increase. So let's say this will be T1, then I measure IL1, T2, then I measure IL2, T3, then I measure IL3, and so on and so forth. And at some point I can then find at some Ti, then I can find basically my maximum current. Okay, and my current, will be the maximum value. That means at some time, after we close the switch, we should be able to, in the experiment, see that we found the maximum current because current doesn't change anymore. Okay. Then if I use this data, I can plot it to find the inductance value. Okay. Because one of the things I can do here is this. At t equals 0, remember, I can assume that as soon as I close the switch at t equals 0, inductor has no current running through that. So in a way, I can find the maximum current. I can relate this to the EMF and divide by the, internal, the EMF of the source. Because one of the things we have here is this. Once the current reaches the maximum value, once that at some t later, right, the current reaches the maximum value, that means the inductor as a device can no longer resist anything, current related, right? Because remember, one of the things we have, there is a potential difference across inductor that is equals to L di dt. So as soon as you reach I maximum, right? As soon as you reach I maximum at some time later, right? Then this di dt basically goes to 0. That means there is no change in current because current reached the maximum value, which means then delta V is equals to 0. That means potential difference across, inductor equals to 0, which means that inductor is no longer acts like a device that resists anything in the circuit. So it just becomes like a wire and nothing else. And that means we can just basically ignore that, and we can say that when the current is maximum, we can use that to rearrange and find the resistance in the circuit, which will be EMF, which is the battery voltage, divided by the maximum current. That's how we can find the resistance. And then if I have a graph where I can linearize it and, for example, plot t time in seconds versus ln of negative IL over I max minus 1, then that data point will give me a straight line. And then the slope of that, according to this equation that we had, right, where time is equals to tau times ln of negative IL over I max minus 1, then if I'm plotting y equals mx, where time is the y-axis, then ln of that whole thing is the x-axis. That means my slope is equal to then the time constant. Once I have the graph, I find the slope, I have the tau, then using this equation, I can find then the resistance value. Then I can relate those two, resistance and the time constant, to this equation where it's equals to L over R. That means from here, inductance is equals to tau times the resistance. And that's my final calculation going to be for the inductor. Again, you take the data of the changing current as a function of time, then plot the time versus ln of negative changing current through the inductor over I max minus 1. The slope is your tau. Find the resistance using EMF, basic maximum voltage divided by maximum current. And then from that, your final calculation will give you the inductor value or the inductance of the inductor. Okay. All right. So that's the first part of the experiment. Second part is kind of similar. What we do is after a very long time, we can then, let's say, open the switch. Okay, so if we open the switch, so let's say here's the battery. All right, so let's say here's a resistor, and then here's the inductor. Okay, so this is R and this is L. This is EMF, and let's say what we have here is this. By the way, one other thing important about the inductor is that inductor is a device that stores magnetic energy. Okay, that means one thing I have here is as soon as I open the switch after the current reached its maximum value, remember, we wait until it's reached its maximum value, and then we open the switch. Remember, an instant before I open the switch, the current was maximum. But now I open the switch, then the current goes from maximum to zero. Or it wants to go from maximum to zero. But there's an inductor in the circuit. An inductor right away resists that. Now in the opposite direction, it's now trying to reinforce the current because the current was maximum, but now we're changing that. So what the inductor will do, again, will induce its own current, its own EMF, and slow down the process of, the decrease of current. So like slow down the instantaneous decrease of current. Current still decreases, but it just, from its maximum value, it doesn't just go straight down to zero. It doesn't just go to zero. Instead of just going straight to zero, it goes exponentially to zero. Okay. That means, again, similar way, we can find then the current through the inductor is equal to now I max, then e to the negative t over tau. That's the equation for the current decrease in the circuit where the inductor basically slows down the rate of the current decrease, instantaneous current decrease. So it still decreases to zero, but it takes a longer time. Okay. Again, we're going to take a data. We're going to, try to analyze this. And what we do here is we're going to, again, similar way, right? Take the ln of both sides. And in this case, what we're going to have, well, first actually divide both sides by I max. So it's going to be ln of IL over I max equals then ln of E negative t over tau. So from here, what we're going to get here is the right side of the equation is going to be negative t over tau, right? Because ln of E to the negative t over tau is just negative t over tau. And then I can see that again, t is equals to negative tau times ln of IL over I max. That means the difference here is there's no longer negative 1. That means we're going to use this again to plot the second data for the decreasing in current. And it's going to be T again versus ln of negative IL over I max. Okay. And again, you're going to get a graph that is going to be linearized because that's how we, plot this. And again, the slope will be equals to your tau. And then you just basically pretty much verify the calculation again, okay, for the inductor. Okay. All right. So in this case, for this second part, we're also going to look at in terms of the, once we find the tau, we can also calculate the resistance of what we call, like, let's say, so in this case, the tau is equals to L over R, but this is going to be the R of a coil plus R of that external load. Now, that equation that I had for the, so technically this equation that I had, this was the resistance for the coil. So we can have that as a resistance of the coil. So then here we're going to calculate the external resistance of that, load resistor. So for that, we'll just basically find the tau and rearrange and use it for that, because now that we already know the inductance value, so our goal here for the second part, where we have a decreasing of current, is to find our external, okay, basically using this equation. All right, so let's look at then the experiment itself. So we're ready to go and look at the experiment. All right, so all right, so here's the experiment. So so we're going to be analyzing the RL circuit, so some preliminary questions, and here's the experimental part. So you can see the same circuits that I had in my whiteboard. So we have the battery, the external resistor, and this is our inductor, the coil. We have a voltmeter and we have an ammeter. Okay. Technically, our devices are battery, resistor, and inductor. Our tools are voltmeter and ammeter, because those are the tools that do not affect the circuit in any way. We just they're used to measure things, but not necessarily, affect the circuit in any way. They're not circuit devices. They are just basically tools that we use for measurements. All right, so here's then the experimental setup. And one of the things we're going to do here, we're going to always then go and use the number 9, trial number 9. You can play with the other ones, but this is going to be the one that we're going to be making measurements with. So you can see that what we have here is, this is our battery, EMF source. This is our switch. Here's our resistor, external. And this is our inductor, L. Where this is the ammeter, measures the current, and this is the voltmeter, measures the voltage. Okay. So our experiment will be based on measurement of the voltmeter and ammeter. So you can see right now, if I make a measurement using volt, you open the switch, you can see that the current doesn't just go to maximum, but slowly goes to the maximum. And then we open the switch, and again, current doesn't go to 0, but goes to 0 slowly. And that's what our measurement is going to be. In terms of here, you can see that we have a voltage, how the voltage changes as a function of time, how the current changes as a function of time, and then already have a pre-built equation for the ln, so that you can plot it and do the graph. So already you can see that all you have to do is just take measurement, and the graph and everything will be directly given to you. So then we have here the same thing. This is for the decreasing current. Again, you have voltage, current times, and negative ln of I over I max, because this is a decreasing. Again, you're going to then use this to find the tau, and use the tau to find the external resistance value. Again, so for example, in terms of just at least one measurement to show you, you can see if I go back here, let's say take out the timer, put it here, and find the instant when the switch is closed right there. So reset, then you can see, right? So let's go back again. It's difficult to work like this. Give me 1 second. Right. Okay, so here's, I think, the instant when we close, reset, and when you play the video, now it's basically gives you current change as a function of time. Okay, that means you go back to 0, and you can say, right, you can see voltage 0, current 0, at time equals 0. And then maybe you can see that as a function of time, it basically goes, the current, right, goes to its maximum, which is roughly, I would say, about 130 or so, or 140. And you can say it takes roughly 4 seconds. So you want to take measurements. I would recommend to take, 10 measurements, even though there's a table for only 5. So make 10 measurements where you can say the time is, let's say, 0, maybe like, let's say then maybe 0.2, 0.4, something like that. Basically, thing like this, 4 seconds divided by 10 measurements. So maybe like every 0.4 seconds or so. So 0.4, 0.8, 1.2, thing like that. And then measure the current. So let's say, what is the current at 0.4 seconds? So you go back and find, or you can see, right, I guess you can't really change it to 0.4 because it increases 0.63, 0.3, let's say, if you can get 0.4. There we go, we can put 0.4. So then the current will be, from here I have 10, 20, 30, about 30, 38 or so milliamps. So you can say that 30, let's say 38 milliamps. You press and you can see, right, already have a data point. Let's say next go to 0.8 in terms of the time. Let's see if we can get 0.8. There you go. What is the current? Current is about, 61 or 62, something like that. So if I go back and do 62 like that, see, I already have a, data points. Don't mind those zeros. That means if I want to populate those, I don't know, let's say 85, something like that, and it'll be 92. You can see, right, maybe like, 120 when the time was 4.2. You can see, right, my data already gives me, so this is like an outlier because I have 0.8, not 8 seconds. There you go. I'm now have more or less linear graph. And I can go curve fit, linear, and have a slope. And that slope is basically my tau. Use that then to find the inductance value. All right. So hopefully it should be, relatively straightforward lab. You just basically measure the voltage, time, and current for each of those 2 experiments, and find the inductance value, find the resistance of the external for the second part, right? Basically, it's explaining in terms of what you need to do. And then there's a table that you can then use to compare your experimental values. All right. Hopefully this was helpful. Feel free to put it in a discussion if you have any questions.